I said many times during the last two sections of the difficulty, if not impossibility, of predicting how a material might behave in terms of its fracture behavior. So my personal interest over many years is, are there ways, let's say fairly simple, straightforward ways of modeling and predicting fracture of materials? If one thinks about it, we're simply pulling atoms apart. And so if we understand the atomistics of a particular material, we should be able to at least come close to predicting the strains, the stresses necessary to pull them apart at a crack tip. And this is particularly important for a number of reasons. First of all, in many cases, as the component that we're interested in, size, single crystals, films, fracture mechanics tests of any kind become very difficult, if not impossible to do. So we would like to have some way of predicting how our material will behave under these conditions. And current test procedures applicable to even small samples, I said earlier, the indentation tests are somewhat lacking in accuracy. And it would be a lot easier, if not maybe more reliable, to be able to predict behavior. And finally, the ability to predict resistance to crack growth would open the door to much more rapid development of new materials with enhanced resistance to fracture. So there are lots of reasons of doing this besides the purely scientific interest of trying to understand what's going on at the atoms in a material as they fracture. So there has been some amount of work done. One of the very early pieces of work was conducted by Gilman and published in 1960. And it's based on the premise, which I think is generally true, that all of the energy to separate the fracture planes when a crack is growing goes into the creation of new surface. This, of course, assumes that there's no plastic flow, there's no temperature, there's no heat dissipated, there are no acoustic events that absorb energy. Probably not all true, but how close can we come? And as it turns out, I think it's relatively accurate under some conditions. And I thought he developed a very clever approach to the problem. He assumed that the bonds between atoms could be represented by a sine function, and derived then the following this expression that you see here for the fracture energy of the material, where now this is elastic modulus of the material, Young's modulus. D0 is the equilibrium distance between the cleavage planes. In other words, here we're assuming the crack moves only in one plane. And A is the distance, and here's the key parameter perhaps that we don't know. A is the distance at which bond rupture occurs. In other words, I'm pulling on the material. Where are those two surfaces formed in pulling on the material? Gilman took A to be the radius of atoms on the cleavage plane, but why is not clear. He gave no basis for that choice. But the form of the equation, I think, is important, and as we go along, I'll try and show that that kind of form seems to be represent one that we can use for other materials as well. So there have been a number of studies that looked at this equation and applied it to single crystals of materials such as the alkyl fluorides or the alkaline earth fluorides and chlorides, and it seems to fit reasonably well, but not clear why. It's fairly good, but there's more complexity than we would like. And just to show that for most materials, fracture toughness and fracture energy are directly proportional to that one term, at least, elastic modulus. Here you see a plot of elastic modulus, Young's modulus, for a whole variety of materials. These can be single crystal or polycrystalline materials. So clearly elastic modulus plays a major role in this, but the other factors do too. So going a little further, and here's where perhaps you can accept or reject some of these ideas. It's ideas that myself and my colleague Jack Machowski had. We published a few years ago. One can derive a more general expression, trying to be simplistic about this. Our ideas, because we were not physicists, but can you derive some simple expression that would allow you to get close to what the fracture energy of a particular material might be with simple knowledge of its elastic behavior and its crystal structure. So the more general expression for gamma, not assuming now a sign function, is that the fracture energy was related to some a numerical constant. Again, this is the d0, the space between cleavage planes. E is Young's modulus. Now there's each function has to have the certain different qualities, namely it has to have an initial slope which comes on the stress-strain curve, which we call Young's modulus. It has to have a maximum stress at some maximum strain because that's where fracture will occur. And it has to have a parameter defining the range of the function. In other words, what distance apart will the bonding function no longer hold. And by definition then, the area under the stress-strain curve that we're talking about is that 2 gamma over d0. So we look to test the idea that this worked with a whole series of materials, and if you look in the literature, there are probably others, but I'll just leave you with this. We chose to look only at cubic systems, trying to simplify what we're endeavoring to examine. So these are the cubic crystal systems that we could find that had fracture energy data, and I give you the references for all of them. And if you look then at the results, here we're plotting then fracture energy that you see here, the same fracture energy we've talked about all along, versus this elastic modulus versus d0, times d0 rather. So this is the expression that I showed earlier. Materials such as potassium chloride, which is the top of that list that I showed just a moment ago, are down in here, and this is diamond up in here. I'll go back and show you. You can look again. So most of the materials fall sort of in the region in here, the fluorides, zinc selenide, and so forth. And up at the top, there's magnesium oxide, silicon, germanium, and so forth. The drawback to this is that there's this whole regime in here where there's really no data that we could find. So there are materials with elastic moduli or d0s that would enhance our ability to make this prediction. But you can see for the at least materials we have, there seem to be the same trend. In other words, we can say that for at least all this set of cubic materials, they all seem to behave in the same way, in the sense that that constant that I talked about in the expression is the same. But here's the rub. Other materials don't behave like this, and maybe that tells us something as well. So if we take this same kind of approach and look at other materials, in this case such as silicon carbide, sapphire, or silica, quartz, they fall off the curve. Why? Is the fracture behavior different than what we see here? Probably. The complexity of the mechanism at the crack tip is much greater than we're taking into account in this very simplistic expression that we're using. So we've talked to numbers of people, and that's really the criticism of what we're trying to do, and we accept that. We're way too simple for what we're trying to achieve. But again, is there some other modeling tool that one can use to get to the heart of the matter of trying to understand what happens at a crack tip as I strain those final bonds that are going to fail during fracture? And one of those mechanisms is called density functional theory. I only mention it because it's one that's the most popular to try and understand fracture modeling. There are numbers of papers out that use this, and I would encourage you to look at this reference, for instance. You can get some good ideas on how far you can go. It requires a lot of quantum mechanical knowledge to use these kind of things, but I think the future will be bring us a lot more understanding using these kinds of approaches, these atomistic approaches to understanding more complex materials. One of the other tools that's used and has been used over the years is termed molecular dynamics, which involves solving Newton's equations of motions for sets of interacting particles. But unfortunately, the exactness of the simulation that you choose is determined by the accuracy of the interatomic potentials that you use. And these are not terribly well known. There's work going on now at NIST, the National Institute of Standards and Technology, to kind of develop some algorithms to determine what are the best models to use for interatomic potentials. And I think that will help to understand how to use this for fracture. So the primary focus for most of these molecular dynamic studies has been amorphous silica, and to lead you to other kind of references. This is a very nice paper, reasonably recent, to say how well this has worked. One of the other attempts that I've made, and my colleagues with me over the years, is trying to model the environmental crack growth behavior. Now I've added one level of difficulty into this, and there's not been much more done on this because of the difficulties in the calculations for all of these kind of behavior. This kind of study now this study itself is fairly old, but the tool we used, namely the molecular orbital theory, was what we had at the time, and I think it gave us some insights into what kind of behavior we were seeing. Molecular orbital theory takes I'll go further and show you what's going on. It takes a small piece of the particular structure, namely a silicon-oxygen bond. This is used a particular calculation scheme called Gaussian 90. It's very old now, but just to show you what could be done if the right tools were available. So you can simulate strains in bending and stretching of silicon-oxygen bonds in what it would be a piece of a structure, a piece of a silicon-oxygen structure. And what this kind of simulation would allow you to do is to calculate the changes in both total bonding and electrons associated with the silicon and oxygen. What it doesn't do is tell you what the whole structure is doing. The criticism, and rightly so, of molecular orbital calculations is that they only take one molecule and don't tell you what's going on in the rest of the lattice associated with this particular molecule, but at least to give you some flavor of what might be going on. What we observed, this from strictly calculations, I kind of hinted at this when I talked about the experimental findings, is that the strain polarizes the silicon and oxygen bonds. In other words, it makes the silicon more positive and the oxygen more negative. It also shown to reduce the number of bonding electrons between the silicon and oxygen. In other words, you're seeing the silicon become more positive and the tendency to bond with the oxygen becomes smaller, which goes in the right direction. We then added environments to these calculations. We added the kind of environments I showed earlier that we showed in experiments, some of which would cause crack growth and some not. And we could find that the molecules that actually did enhance crack growth had the lowest calculated energy on approaching the silicon-oxygen-silicon bond, and that those energies reduced by bond strain. So not only did they tend to make the molecules want to react with the silicon-oxygen bond, but they kind of pulled the molecule into the crack tip. So in other words, they produced an enhanced crack growth because reducing the steric hindrance on restricting the environment's approach to the crack tip, as well as reacting with the crack tip bond itself. And then you could go further because of what I said earlier about silicon showing no crack growth. The calculations indicated that the strain produced no polarization in the silicon-silicon bond, and it suggested that steric hindrance and no separation of charge here would agree with the idea that we saw no change in crack growth behavior in water, even at significant strains. And again, this is in agreement with what we showed earlier from experiment. So let me just summarize this very short summary of where we are, which is not very far. That models assume that all the strain energy put into a system when you're modeling goes into the formation of fracture, and that no energy is lost to heat, acoustics, or plastic deformation. Probably not a very good assumption, but if you don't make it, I think it's going to be very hard to go any further in this, but this is what we've looked at. Current modeling methods, I've tried to say, although yielding interesting results, are way too simplistic to yield accurate predictions of the fracture of real materials. And I am encouraged by the idea that as computing power increases, then more sophisticated quantum mechanical techniques will become available, and the models for predicting fracture will become better and more accurate. I think that's going to be important as our materials that we use become more complex and smaller in extent as we move from the kind of materials world that we see here to that of nanomaterials. It's going to be increasingly important to be able to have some idea, some prediction and idea of how these materials will behave, and testing of these materials on any easily accessible scale will be very difficult. And then let me just conclude in this section by giving you a number of other references which you should look at, and some very nice work by Peter Gumsch and so forth. And there are a lot more than this that will lead you to other ideas. So that will conclude our discussion of modeling for now, and hopefully this will move further in the near future.